Hello friends, today I am discussing about the most important chapter of science class 9, from which minimum 2 say 3 questions are asked in every exam, so it is most important. So let's start without wasting of times. Chapter is 4. Chapter name is structure of the atom. Let's start. In chapter 3 we have learned that atoms and molecules are the fundamental building block of matter. We have learned that atoms and molecules are the fundamental building block of matter. The existence of different kinds of matter is due to different atoms constituting them. Now the questions arise: 1. What makes the atoms of one element different from the atoms of another element? Next question is, are atoms really individual as proposed by Dalton, or are there smaller constituents inside the atom? We shall find out the answer to these questions in this chapter. We will learn about subatomic particles and the various models that have been proposed to explain how these particles are arranged within the atoms. A major challenge before the scientists at the end of 19th century was to reveal the structure of the atom as well as to explain its important properties. The elucidations of the structure of atoms is based on a series of experiments. One of the first indications that atoms are not indivisible comes from studying static electricity and the condition under which electricity is conducted by different substances. Next, charged particles in matter. For understanding the nature of charged particles in matter, let us carry out the following activities. Activity 4.1. A comb dry hair. Does the comb then attract small pieces of paper? B. Rub a glass rod with a silk cloth and bring the rod near an inflated balloon. Observe what happens. From these activities, can we conclude that on rubbing two objects together, they become electrically charged? Where does this charge come from? This question can be answered by knowing that an atom is divisible and consists of charged particles. Many scientists contributed in revealing the presence of charged particles in an atom. Okay. It was known by 1900 that the atom was indivisible particle but contained at least one subatomic particle, the electronic, identified by J.J. Thomson. It was known by 1900 that the atom was indivisible particle but contained at least one subatomic particle, the electron, identified by J.J. Thomson. Okay. Even before the electron was identified, E. Goldstein in 1886 discovered the presence of new radiation in a gas discharge and called them canal ray. Even before the electron was identified, E. Goldstein in 1886 discovered the presence of new radiation in a gas discharge and called them canal ray. Got it? These rays were positively charged radiation which ultimately led to the discovery of another subatomic particle. Okay. This subatomic particle had a charge equal in magnitude but opposite in sign to that of the electron. The subatomic particle had a charge equal in magnitude but opposite in sign to that of the electron. Its mass was approximately 2000 times as that of the electron. It was given the name of proton. In general, an electron is represented as E- and proton as P+. Its mass was approximately 2000 times as that of the electron. It was given the name of proton. In general, an electron is represented as E- and proton P+. The mass of a proton is taken as 1 unit and its charge as +1. The mass of an electron is considered to be negligible and its charge is -1. Got it? It seemed that an atom was composed of protons and electrons, mutually balancing their charge. It also appeared that the protons were in the interior of the atom, for whereas electron could easily be removed off, but not protons. It seemed that an atom was composed of protons and electrons. Okay. Mutually balancing their charge. It also appeared that the protons were in the interior of the atom, for whereas electron could easily be removed off, but not protons. Okay. Now the big question was, what sort of structure did these particles of the atom form? We will find the answer the questions below. Okay. The structure of an atom. We have learnt Dalton atomic theory in chapter 3, which suggested that the atom was indivisible and indestructible, but the discovery of two fundamental particles, electrons and protons, inside the atom led to the failure of this aspect of Dalton atomic theory. Dalton atomic theory, in which suggested that the atom was indivisible and indestructible, but the discovery of two fundamental particles, electrons and protons, inside the atom led to the failure of this aspect of Dalton atomic theory. It was then considered necessary to know how electrons and protons are arranged within an atom. For explaining this, many scientists proposed various atomic models. J.J. Thomson was first one to propose a model for the structure of an atom. J.J. Thomson was the first one to propose a model for the structure of an atom. Okay. Now we will discuss about Thomson model of an atom. Okay. Thomson proposed the model of an atom to be similar to that of a Christmas pudding. The electrons in a sphere of positive charge were like currents, dry fruits in a spherical Christmas pudding. Thomas proposed the model of an atom to be similar to that of a Christmas pudding. The electrons in a sphere of positive charge were like currents, dry fruits, okay, in a spherical Christmas pudding. Okay. Then we can also think of a watermelon. The positive charge in the atom is spread all over like the red ideal part of the watermelon, while the electrons are studied in the positively charged sphere like the seeds in the watermelon. Now We can also think of a watermelon. The positive charge in the atom is spread all over like the red edible part of the watermelon, while the electrons are studied in the positively charged sphere like the seed in the watermelon. Figure 4.1, Thomson model of an atom. Here is electron, here is a positively charged. Okay, got it? J.J. Thomson, 1856 to 1940, a British physicist, was born in Chatham Hill, a suburb of Manchester on 18 December 1856. He was awarded the Nobel Prize in Physics in 1906 for his work on the discovery of electrons. He directed the Cavendish Laboratory at Cambridge for 35 years, and 7 of his research assistants subsequently won a Nobel Prize. J.J. Thomson, he directed the Cavendish Laboratory at Cambridge for 35 years, and 7 of his research assistants, okay, subsequently won Nobel Prize. Now we will discuss about Thomson proposed that, okay. Thomson proposed that, first, an atom consists of a positively charged sphere and the electrons are embedded in it. Next, the negative and positive charge are equal in magnitude, so the atom as a whole is electrically neutral. Okay. Although Thomson model explained that atoms are electrically neutral, the result of experiments carried out by other scientists could not be explained by this model, as we will see below. Okay. Rutherford is model of an atom. Ernest Rutherford was interested in knowing how the electrons are arranged within an atom. Okay. Rutherford designed an experiment for this. In this experiment, fast moving alpha particles were made to fall on a thin gold foil. Rutherford designed an experiment for this. In this experiment, fast moving alpha particles were made to fall on a thin gold foil. He selected a gold foil because he wanted as thin a layer as possible. This gold foil was about 1000 atoms thick. Okay. Alpha particles are doubly charged helium ions since they have a mass of 4 units. The fast moving alpha particles have a considerable amount of energy. It was expected that alpha particles would be deflected by the subatomic particles in the gold atoms. Since the alpha particles were much heavier than the protons, he did not expect to see large deflections. Okay. Here figure 4.2, a scattering of alpha particles by a gold foil. But the alpha particles scattering experiment gave totally unexpected results. Figure 4.2, the following observations were made. First, most of the fast moving alpha particles passed straight through the gold foil. Okay. Next, some of the alpha particles were deflected by the foil by small angles. Yes. Then, surprisingly, 1 out of every 12,000 particles appeared to be rebound. In the words of Rutherford, this result was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it comes back and hits you. Okay. Now we will know about Rutherford. E. Rutherford, 1871 to 1937, was born at Spring Grove on 30 August 1871. He was known as the father of the nuclear physics. Rutherford was known as the father of nuclear physics. He is famous for his work on radioactivity and the discovery of the nucleus of an atom with the gold foil experiment. He got the Nobel Prize in Chemistry in 1908. Okay. Let us think of an activity in an open field. To understand the implications of this experiment, let a child stand in front of a wall with his eye closed. Let him throw stones at the wall from a distance. Okay? He will hear a sound when each stone strikes the wall. If he repeats this 10 times, he will hear the sound 10 times. But if a blindfolded child were to throw stones at a barbed wire fence, most of the stone would not hit the fencing and no sound would be heard. This is because there are lots of gaps in the fence which allow the stones to pass through them. Following a similar reasoning, Rutherford concluded from a alpha particle scattering experiment that first, most of the space inside the atom is empty because most of the alpha particles passed through the gold foil without getting deflected. Second, very few particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. Okay, next, a very small fraction of alpha particles were deflected by 180 degree, indicating that all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. Okay. From the data, he also calculated that the radius of the nucleus is about 10 to the power 5 times less than the radius of the atom. From all the data, he also calculated that the radius of the nucleus is about 10 to the power 5 times less than the radius of the atom. Okay. On the basis of his experiment, Rutherford put forward the nuclear model of an atom, which had the following features. First, there is a positively charged center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. Next, the electrons revolve around the nucleus in a circular path. Okay. The size of the nucleus is very small as compared to the size of the atom. Got it. Drawback of Rutherford model of the atom. The revolution of the electrons in a circular orbit is not expected to be stable. The revolution of the electron in a circular orbit is not expected to be stable. Okay. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particle would radiate energy. Okay. Thus, the revolving electron would lose energy and finally fall into the nucleus. Okay. If this were so, the atom should be highly unstable and hence matter would not exist in the form that we know. We know that atoms are quite stable. If this were so, the atom should be highly unstable and hence matter would not exist in the form that we know. We know that atoms are quite stable. Okay. Now we will discuss about Bohr's model of atom. In order to overcome the objection raised against Rutherford model of the atom, Niels Bohr put forward the following postulates about the model of an atom. First, only certain species orbit known as discrete orbits of electrons are allowed inside the atom. First, only certain special orbit known as discrete orbits of electrons are allowed inside the atoms. Okay. While revolving in discrete orbit, the electrons do not radiate energy. Now, we can know about Niels Bohr. Niels Bohr, 1885 to 1962, was born in Copenhagen. On 7 October 1885, he was appointed professor of physics at Copenhagen University in 1960. He got the Nobel Prize for his work on the structure of atom in 1922. Among Professor Bohr's numerous writings, three appearing as book are: first book, The Theory of Spectra and Atomic Constitution. Second book is Atomic Theory, and third book is The Description of Nature. No. These orbits or cells are called energy. Okay. Energy level in an atom are shown in figure 4.3. Okay. These orbits or cell are represented by the letters K, L, M and so on, or the numbers n equal to 1, 2, 3, 4. Here n cell, M cell, L cell, K cell and a nucleus in figure 4.3. For K cell n equal to 1, L cell n equal to 2, M cell n equal to 3 and N cell n equal to 4. Okay. Neutrons. In 1932, J. Chadwick discovered another subatomic particle which had no charge and a mass nearly equal to that of a proton. It was eventually named as neutron. In 1932, J. Chadwick discovered another subatomic particle which had no charge and a mass nearly equal to that of a proton. It was eventually named as neutron. Okay. Neutrons are present in the nucleus of all atoms except hydrogen. Neutrons are present in the nucleus of all atoms except hydrogen. In general, a neutron is represented as n. The mass of an atom is therefore given by the sum of the masses of protons and neutrons present in the nucleus. In general, a neutron is represented as n. Okay. The mass of an atom is therefore given by the sum of the masses of the proton and neutrons present in the nucleus. Okay. Now, we will discuss about how are electrons distributed in different orbits cells. Okay. The distribution of electrons into different orbits of an atom was suggested by Bohr and Bury. The following rules are followed for writing the number of electrons in different energy level or cells. First, the maximum number of electrons present in a cell is given by the formula 2n square, where n is the orbit number or energy level, index 1, 2, 3. Hence, the maximum number of the electrons in different cells are as follows. First orbit or K cell will be 2 into 1 square equal to 2. Second orbit or L cell will be 2 into 2 square equal to 8. Third orbit or M cell will be 2 into 3 square equal to 18, and fourth orbit or N cell will be 2 into 4 square equal to 32, and so on. Second, the maximum number of electrons that can be accommodated in the outermost orbit is 8. Okay. Electrons are not accommodated in a given cell unless the inner cell are filled, that is, the cell are filled in a stepwise manner. Okay. Atomic structure of the first 18 elements is shown schematically, figure 4.4. Here, figure 4.4, schematic atomic structure of the first 18 elements. Okay. Now, activity 4.2, make a static atomic model displaying electronic configuration of the first 18 element. Yes. The composition of atoms of the first 18 element is given in table 4.1. Now we will discuss about valency. We have learned how the electrons in an atom are arranged in different cells orbit. The electrons present in the outermost cell of an atom are known as the valency electrons. We have learned how the electrons in an atom are arranged in different cells orbit. The electrons present in the outermost cell of an atom are known as the valency electrons. From the Bohr-Bury scheme, we also know that the outermost shell of an atom can accommodate a maximum of 8 electrons. It was observed that the atoms of elements completely filled with 8 electrons in the outermost shell show little chemical activity. In other words, their combining capacity or valency is 0 of these inert elements. In other words, their combining capacity or valency is 0 of these inert elements. The helium atom has 2 electrons in its outermost shell, and all other elements have atoms with 8 electrons in the outermost shell. Okay. The combining capacity of the atoms of elements, that is, their tendency to react and form molecules with atoms of the same or different elements, was thus explained as an attempt to attain a fully filled outermost shell. Okay. An outermost shell which had 8 electrons was said to possess an octet. Atoms would thus react so as to achieve an octet in the outermost shell. An outermost shell which had 8 electrons, was said to possess an octet. Atoms would thus react so as to achieve an octet in the outermost shell. This was done by sharing, gaining, or losing electrons. The number of electrons gained, lost, or shared so as to make the octet of electrons in the outermost shell gives us directly the combining capacity of the elements, that is, the valency discussed in the previous chapter. For example, hydrogen, lithium, sodium atoms contain 1 electrons each in their outermost shell. Therefore, each one of them can lose 1 electron. So they are said to have valency of 1. Can you tell what is valency of magnesium and aluminum? It is 2 and 3 respectively, because magnesium has 2 electrons in its outermost shell and aluminum has 3 electrons in its outermost shell. Okay. If the number of electrons in the outermost shell of an atom is close to its full capacity, then valency is determined in a different way. For example, the fluorine atom has 7 electrons in the outermost shell and its valency could be 7, but it is easier for fluorine to gain 1 electron instead of losing 7 electrons. Hence, its valency is determined by subtracting 7 electrons from the octet, and this gives you a valency of 1 or 1 for fluorine. Valency can be calculated in a similar manner for oxygen. What is the valency of oxygen that you get from this calculation? Therefore, an atom of each element has a definite combining capacity called its valency. Of the first 18 elements is given in the last column 4.1. Okay. Here, table 4.1, composition of atoms, the first 18 elements with electron distribution in various shells. Name of element, symbols, atomic number, number of protons, number of neutrons, number of electrons, distribution of electrons KLM, N, and valency. Hydrogen H, atomic number 1, number of protons 1, number of neutrons 0, number of electrons 1, distribution of electrons K1, L no, M no, N no, valency is 1. Similarly, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, so on. You can look it. Okay. Now, we will discuss about atomic number and mass number. Atomic number. We know that protons present in the nucleus of an atom. It is the number of protons of an atom which determine its atomic number. It is denoted by Z. All atoms of an element have the same atomic number Z. In fact, elements are defined by the number of protons they possess. Atomic number. We know that protons are present in the nucleus of an atom. It is the number of protons of an atom which determines its atomic number. It is denoted by Z. All atoms of an element have the same atomic number Z. In fact, elements are defined by the number of protons they possess. For hydrogen, Z equal to 1. Because in hydrogen atom, only one proton is present in the nucleus. Similarly, for carbon, Z equal to 6. Therefore, the atomic number is defined as the total number of protons present in the nucleus of an atom. The atomic number is defined as the total number of protons present in the nucleus of an atom. Now we will discuss about mass number. After studying the properties of subatomic particles of an atom, we can conclude that mass of an atom is practically due to protons and neutrons alone. These are present in the nucleus of an atom. Hence, protons and neutrons are also called nucleons. We can conclude that mass of an atom is practically due to protons and neutrons alone. These are present in the nucleus of an atom. Hence, protons and neutrons are always called nucleons. Therefore, the mass of an atom resides in its nucleus. For example, mass of carbon is 12U because it has 6 protons and 6 neutrons. 6U plus 6U equal to 12U. Similarly, the mass of aluminum is 27, 13 protons plus 14 neutrons. The mass number is defined as the sum of the total number of protons and neutrons present in the nucleus of an atom. It is denoted by A. In the notation of an atom, the atomic number, mass number and symbol of the element are to be written as mass number, symbol of element, atomic number. Here X is symbol of element and A is mass number and Z is atomic number. For example, nitrogen is written as N14A mass number and 7Z atomic number. Now we will discuss about isotope. In nature, a number of atoms of some elements have been identified which have the same atomic number but different mass number. Isotopes. A number of atoms of some elements have been identified which have the same atomic number but different mass number is called isotopes. For example, take the case of hydrogen atom. It has 3 atomic species, namely protium 1H1, deuterium 1H2 or D, and tritium 1H3 or T. The atomic number of each one is 1, but the mass number is 1, 2 and 3 respectively. Other such examples are carbon 6C12 and 6C14, and second chlorine 17Cl35 and 17Cl37 etc. On the basis of this example, isotopes are defined as the atoms of the same element having the same atomic number but different mass number. On the basis of these examples, isotopes are defined as the atoms of the same element having the same atomic number but different mass number. Therefore, we can say that there are 3 isotopes of hydrogen atom, namely protium, deuterium and tritium. Many elements consist of a mixture of isotopes. Each isotope and element is a pure substance. The chemical properties of isotopes are similar, but their physical properties are different. Here is an important fact. Many elements consist of a mixture of isotopes. Each isotope of an element is pure substance. The chemical properties of isotopes are similar, but their physical properties are different. Okay. Chlorine occurs in nature in two isotopic forms with masses 35U and 37U in the ratio 3:1. Obviously, the question arises, what should we take as mass chlorine atom? Let us find out. Of course, the average atomic mass of chlorine atom on the basis of the above data will be 35 into 75 by 100 plus 37 into 25 by 100 equal to 105 by 4 plus 37 by 4 equal to 142 by 4 equal to 35.5 U. The mass of an atom of any natural element is taken as the average mass of all naturally occurring atoms of that element. If an element has no isotopes, then the mass of its atom would be the same as the sum of protons and neutrons in it. But if an element occurs in isotopic forms, then we have to know the percentage of each isotopic form and then the average mass is calculated. This does not mean that any one atom of chlorine has fractional mass 35.5 U. It means that if you take a certain amount of chlorine, it will contain both isotope of chlorine and the average mass is 35.5 U. Applications. Since the chemical properties of all the isotopes of an element are the same, normally we are not concerned about taking a mixture, but some isotopes have special properties which find them useful in various fields. Some of them are: first, an isotope of uranium is used as a fuel in nuclear reactor. Here is important fact: an isotope of uranium is used as a fuel in nuclear reactor. Second, is this also important fact: an isotope of cobalt is used in the treatment of cancer. Next, an isotope of iodine is used in the treatment of goiter. Now we will discuss about isobars. Let us consider two elements. Calcium atomic number is 20 and argon atomic number is 18. The number of protons in these atoms is different, but the mass number of the both these elements is 40. That is, the total number of nucleons is the same in the atoms of this pair of elements. Atoms of different elements with different atomic numbers which have the same mass number are known as isobars. Atoms of different element with different atomic number which have the same mass number are known as isobars. Got it? Now we will discuss about what you have learned. This is actually important fact, so you mug up it. Credit for the discovery of electrons and protons goes to J.J. Thomson and E. Goldstein respectively. Credit for the discovery of electron and proton is J.J. Thomson and E. Goldstein respectively. J.J. Thomson proposed that electrons are embedded in a positive charge. Rutherford is alpha particles scattering experiment led to the discovery of the atomic nucleus. Rutherford's model of the atom proposed that a very tiny nucleus is present inside the atom and the electrons revolve around this nucleus. The stability of the atom could not be explained by this model. Niels Bohr's model of the atom was more successful. He proposed that electrons are distributed in different cells with discrete energy around the nucleus. If the atomic cells are complete, then the atom will be stable and less reactive. Next, James Chadwick discovered presence of neutrons in the nucleus of an atom. So the three subatomic particles of an atom are first electrons, second protons and neutrons. Electrons are negatively charged, protons are positively charged and neutrons have no charge. Okay. The mass of an electron is about 1 by 2000 times the mass of an hydrogen. The mass of a proton and a neutron is taken as 1 unit each. The mass of an hydrogen atom, the mass of a proton and a neutron is taken as 1 unit each. Cell of an atom are designed as KLMN. Valency is the combining capacity of an atom. Okay. The atomic number of an element is the same as the number of protons in the nucleus of its atom. The mass number of an atom is equal to the number of nucleons in its nucleus. Okay, next. Isotopes are atoms of the same element which have different mass number. Okay. Isobars are atoms having the same mass number but different atomic number. Elements are defined by the number of protons they possess. Got it? It is most important, so you mug up it. No hair exercise. No. This video is end. So friends, thank you for watching this video. Hope you will be learn on new things. Thank you so much. Bye bye, take care.